Okay, let's get going. Remember that we derived these three equations, and once again I'd like to emphasize that it's rectilinear and constant acceleration. Otherwise these equations are not valid, so be careful. One more thing that I didn't mention is the equation for the average velocity, and there are two ways in which you could write that. Anybody, what do you think is the, based on the variables that we have here, which are the 5 variables V, U, A, S and T, can you define the average speed? Under these conditions, rectilinear, constant acceleration, what is the average speed? You can use any one of these variables. Any, more than one as well, of course. In fact, you can take two at a time and you can define, yes.
Are you saying take two of the variables?
Yeah, yeah, take any two of these and define the average speed.
So would it be like velocity over delta t? Is that what you're looking for, or something more specific?
Velocity or delta t is not a velocity, right? This is a velocity, this is a speed. So it should have the same unit as velocity, first of all. So if you divide by time, it will no longer be a velocity, it will become like an acceleration, right?
So then, would it be acceleration divided by, wait, I don't think I understand.
Can you just do S over T?
That's, yeah.
S over T, yes. So that's one way of defining it, because remember that we are starting with from t equal to t naught we have taken as 0. S is equal to S naught which we have taken as 0. So distance S is covered in a time t. So that is one way of looking at the average speed. Another way?
V plus U by 2.
Yeah. So 1/2 of the initial speed and the final speed is the average. In fact, that's the original way in which the average speed is, any average is defined if it's a constant. So once again, you can see if you plot, let's say, the velocity v versus time. So it starts off at t equal to 0 with u, and if it's accelerating with a positive acceleration, then it becomes a larger value v at some instant of time t, and so you're talking of a straight line over there, right? And which is why it's a constant acceleration, because the slope of this line is what the acceleration is all about, right? So this is the slope equal to A, right? So by substituting this into some of these, you can have various forms of the same set of equations. So it's a question of just manipulating with these 5 variables. So depending upon how the problem is essentially put to you, how it is described, you can identify from there which are the things which are given, which are not given, and choose the appropriate set of equations to solve for it. But don't use it for when the acceleration is not constant, or when you're dealing with motion that is not rectilinear. So restrict yourself to just these. Yeah. So just before we broke for lunch, we looked at this previous slide where we looked at 4 different ways of dealing with a situation when acceleration is not a constant. So in other words, we still have rectilinear motion, but we can have any arbitrary acceleration which we said is a of t, any function of time. And then there are many ways in which you could determine the other variables, and we specified 4 different paths equivalent of each other. 2 using integrals, 2 using initial value problems. The ones using integral were different in the sense one was definite integrals, the other used indefinite integrals. In terms of the initial value problem, either first order with a set of equations, 2 equations in the set, and the other one is just a single equation but second order. In other words, the highest derivative which appears in the equation is second order. Right? Now we will go to the next level of complication. So this is the simplest, where we have constant, Then you have a function a of t, but function only of t explicitly. Now we will bring in a as a function of not only t, but also r and v in general, which will still is rectilinear motion, but the more general version of it. So as in when we go to the more and more general versions, these are going to be applicable to the simpler versions we started off with as well. Okay, so we are just generalizing the problem so that you can apply the same thing what we are going to study on this slide for the simplest case of constant acceleration, or a as a function only of time and not explicitly of the other two variables. The other two variables we are bringing in other than time that acceleration is a function of is your r of t, the position vector that you're looking at, and then you're also looking at r dot of t, which is another way of looking at the velocity. Because it's a rectilinear motion, it's as simple as just saying r dot of t, because we're only concerned about the measure numbers, that is the position and the speed along that line, which we are interested in. So once again, the differential equation alone is not sufficient. The differential equation is r double dot. Of course, once again, we can pose the problem in those 4 different ways. Since they are all equivalent of each other, no point in again and again talking about the same thing. So I'm just taking the 4th example method that we had, which is using a second order differential equation, a single equation, and trying to solve the problem. The only complication from then to now is to see that these two are appearing within the acceleration. In other words, they are functions of the positions. For example, you say from after you have covered a certain distance, you're till then you're not accelerating, and maybe you're accelerating after that. Or in a typical road kind of a scenario, you can involve the speed breakers, the traffic signals, etc., and then cover that, or the speed limits that are there in different locations. Based on that, you can have discrete functions of acceleration, or you could have continuous functions as well. For example, most vehicles are advertised based on their acceleration from 0 to 100 miles per hour. What is the time it takes to get to there? So something like that. But beyond that, the acceleration will come down or go up depending upon how the drive is. So up to certain limits, of course. And then all of that can be incorporated in this kind of a function, and then you can see how the second order differential equation can be solved along with its initial conditions, which are exactly same as what you had on the previous slide when you had a as a function only of time. Even then you had the initial position r naught and the initial speed v naught. Without loss of generality, as we saw, we could take this as 0, for example, but this will have to be specified what is the speed. So this is just to set the datum where you're starting the count as far as s is concerned or t is concerned. So that's up to us to define that. Okay, and whatever we give, it comes out in terms of that. Then depending upon exactly how this function is actually constructed or given to us, this could be a nonlinear equation, because remember, in this equation the unknown quantity is r, okay, whose second derivative is appearing as a power 1 in the left hand side. So from that it seems like a linear equation, but the same r is appearing as without the dots and with just a single dot on the right hand side. So when you're testing for the linearity or a non-linearity of a differential equation in terms of an unknown quantity, we have to check for the not only the highest derivative but also the lesser derivatives and the function itself, in what powers are they appearing throughout. So if they're all either power 1 or 0, which means a constant term or a term which is a function only of time, then you have a linear differential equation. On the other hand, if they appear as products, let's say r times r dot, or as r squared or r dot squared, etc., or some other function of r, let's say sine r or whatever, then all of these are going to become the entire equation is said to be a nonlinear differential equation that you are dealing with, making it even more complicated. Okay, so if it's a linear differential equation, more often than not you should be able to solve this even in an analytical form. But if it gets into nonlinear equations, there might be exceptions, a few which can still be solved analytically, but more often than not you will have to get into numerical solutions because it's not feasible to get analytical solutions. Okay, So what if the acceleration is function, as I said, is a function of r and v. So that v is what we are putting as r dot of t, because it's very simple straight line motion, the rectilinear motion that we are looking at. And therefore we can put everything in terms of r, which is why v is replaced with r. You can continue to deal with it as, let's say, v dot and r dot, and treat it as a set of two equations, and then you try to solve them simultaneously, which is the third kind of problems that we already talked about. Okay, then okay, let me go to the next slide. Are there any questions on this? You see how this can bring in the complication into the problem, right? That's always the takeaway from this slide. So as I said, since analytical solutions are not possible, you have to get into numerical solutions, and numerical methods of solving the differential equations, in fact, occupies a whole lot of computational power today. Knowingly or unknowingly, most of the people are using, in fact, the most powerful computers, including supercomputers, for primarily solving these differential equations. In fact, an estimate a few years ago said that about more than 50% or half of the supercomputer power is actually being utilized to solve differential equations for various problems. Right now, there are also analytical, semi-analytical, and also numerical methods which can be done using symbolic processors like Maple or Mathematica. Mathematica, for example, if you want to solve a differential equation analytically, it has the command dsolve without the n. And if you see that it's not able to solve it, you can go for an ND-solve, where n stands for the numerical and d is the differential. So differential equation solver with numerical, and you essentially do an ND-solve. So there are equivalent commands in Maple and other symbolic processing software as well. For example, MATLAB has this ODE445, which will do it for you. These are not the only ones, but these are examples of that. In the next homework that you're going to present this Thursday, one of the problems is about the Falcon 9. It's a rocket, and of course the problem is posed in a very, very simplified way, so that beginners in dynamics can actually solve that kind of a problem without much of a difficulty. But in reality, what is there are a lot of assumptions which go into before posing the problem in that way. For example, of course, some are valid. For example, it is a low Earth orbit, so LEO, which is a reasonable thing to know, because that's what it is. On the other hand, certain assumptions about the payload and how it varies, because remember that for the first stage, you have the rest of the rocket, including the higher stages, as the payload. Whereas once you get to the highest stage, it's only the whatever it's carrying, let's say the satellite which it wants to deploy, as the payload. So it's changing in a discrete sense. So that has to be accounted for. Then in order to solve a realistic problem, you'll need a lot of data, which may not be given in a simplistic version of the problem, like what you're talking about in terms of data, like the entire mass distribution in the vehicle, where the fuel is, so essentially the propellant that you're talking about over there, which is the oxidizer plus the fuel mixed together. If it's a solid propellant, or if it's a liquid propellant, then you have it in separate tanks, and then they are mixed and ignited, right? So you'd have the empty weight, how it's distributed, mostly structural weight. Then of course all the joints and other things between stages or within the stage as well. Then you're talking about the fuel, and of course by which I mean the propellant, actually the payload, right? Then you come to the thrust. Of course you could have booster rockets, so they are, and how they are mounted and other things that can also cost various things. Then there's the thrust, in terms of how its history is, in terms of what's the maximum thrust you can reach, how you arrive at the maximum thrust starting from zero, what is the specific impulse involved, what's the burn time for the entire propellant, depending upon the internal configuration of the propellant, whether it's star shape or whatever, depending on that, how quickly it burns up for a solid propellant. Similar things for the liquid propellant as well. Then you have the computational simulation mathematical models that are there, which will be able to, even if based on some of the experimental data or tests that are done, both on flight and or based on sensors on flight, or the scaled down versions that you might do it at a lab level. Based on that, you have certain mathematical models for each one of these quantities, like the fuel burn rate, the thrust as a function of both the altitude as well as the fuel burn, gravity, because remember that this is going through a fairly large altitude shift, starting probably from close to mean sea level, depending on which location it is launched from. It will go all the way up to a certain altitude where it is deploying the satellite. So you see that the acceleration due to gravity itself due to the Earth will change, and if it is eventually going for an interplanetary mission or something, the gravity of the other planetary bodies or satellites will also come into picture, like the moon, etc. Then the aerodynamic model that you should have, what is the drag that is it is incurring depending upon the shape of the rocket itself initially, and of course after some of the earlier stages have been jettisoned. What is the remaining part of the rocket, what is the drag that it undergoes. Of course that is of significance only as long as the atmosphere is significant. Once you reach rarefied regions, the drag will not be such an important part. There are also these re-entry vehicles, so you'll have to look at the other end of the spectrum, and there is huge heating because of the re-entry and things like that. So the reason why I'm bringing this up is we are studying dynamics in an isolated way as rigid body dynamics, but you should never lose the bigger picture, the holistic picture of where it actually is going, and therefore the other courses that you're doing will all come in handy in terms of doing a realistic problem eventually. Okay, but as a pedagogical tool, it's good to make certain assumptions, leave out the other complications, not overly complicate the problem, so that you understand the specifics of this particular subject, and you understand all the equations involved, how you're going to solve that. Okay. So now that I think you have all the tools for doing Thursday's homework, let's venture into a little beyond that, so that the homework that is due from next week onwards, every Monday and Thursday, you will be able to handle it as well. So one of the things that you will experience as we go forward is the before we get into 3D rigid body motion, which is a little more complicated because of rotations, we will start with 3D particle. So instead of looking at it in two steps, going from 1D to 2D and then 3D, right away I'm jumping into 3D, because 2D can then be dealt with as a special case. So can 1D be. Okay. Now, as always, we are making something knowing fully well that it is kind of a dicey thing, inertial frame of reference, but without that we cannot proceed further, because we don't know any laws governing in a non-inertial frame of reference. So we will take it, and for the right reasons, because from an engineering point of view it is good enough. So then to start with, as I said, always we are going to introduce the frame of reference, we are going to introduce the coordinate system, we are going to introduce the unit vectors. This is how we start each and every problem. So the coordinate system that we will choose is the simplest coordinate system that we are very familiar with. We have utilized it for so many other courses. So that's the Cartesian coordinate system, named after René Descartes, and it's essentially mutually orthogonal dextral triad. So you cross any two of them, you should get the other one, either positive or negative depending on the order, and you have a set of unit vectors associated with them. Because it is Cartesian, these are straight lines, the unit vector is not going to be a function of x, y, and z. It's going to be just constant values throughout the entire space or domain that you are interested in solving this problem for. So that's the main thing that we're getting into, and you will see many of the things that we have already considered as special cases of that. Okay, so when you have this particle which is moving in an arbitrary three-dimensional space, you are going to obviously need vectors to work with. Remember that we were talking of these functions a of t, r of t, v of t, etc., as if they were scalar quantities, which was fine for that problem that we were dealing with, the rectilinear motion with or without constant acceleration. We were able to handle that, no issues. Okay, but once we get into 3D motion, or even for that matter 2D motion in between, we will have to go back to what they really are. Each one of these, be it the position or the you're talking about the velocity or the acceleration, they're all vectors, have a certain magnitude, which is what was only important in the previous slides and in the morning session that we had. But now the direction also becomes important. So no longer a scalar, it's a vector, right? Now coming to the position vectors to start with, then we get into velocity and acceleration, because position vector is what we always start with, is the simplest thing. Of course, the problem itself can be posed in an indirect way, in a reverse direction. Okay, so if you have the position vector, then obviously in a Cartesian coordinate system, it's very simple. As I said, I hat, j hat, and k hat are tangential to the x-axis, the y-axis, and the z-axis. And because these are straight lines in a Cartesian system, therefore I hat, j hat, and k hat are not functions of time. Okay, it's only the measure numbers x of t, y of t, and z of t, which are measure numbers and functions of time, right? So whereas if you introduce a system which is a curvilinear coordinate system instead of a Cartesian coordinate system, then not only x, y, and z will be functions of time, but your I, j, and k will also be functions of time, and you have to have the chain rule or the product rule that is utilized over there. Now that we have the advantage of I, j, k being constants, very easily we can get to the velocity by just taking the derivatives of x, y, and z, and again multiplying them with I, j, and k respectively, and then you get the velocity vector, which is r dot of t, right? Similarly, the acceleration is one more level of differentiating the position vector, that is, or first derivative of velocity, it's the second derivative of the position vector. So this is how we can get to each one of them, and you will see examples of that when you work out some of your problems, especially for the next homework, not this Thursday's, but Monday's homework. Okay. Now these time derivatives that you see, these notations that I'm using with just the dots, etc., is quite vague. As remember that when we are writing it as d by dt, we used to put a pre-superscript which said which frame are we taking that with respect to. So that is very important. So in this case, it's assumed that it's the default frame with respect to which it is taken, the frame on which I, j, and k are fixed. Okay, so your I, j, k, the coordinate system was fixed into a particular inertial frame of reference. You assume that frame is inertial, and then you said that let's call it I. And so all of these dots, whether it's r dot or v dot or r double dot, these are all with respect to that frame of reference. Yeah. So of course the dot means it's a derivative with respect to time, but taken with respect to a particular frame of reference, and that frame of reference, unless specified explicitly, is the default frame, which is the inertial frame of reference, and in this case the one in which I, j, and k are fixed. Okay, so you have this particle p which is moving. Okay, and we will come to its mass and other things later when we look at the kinetics. Right now we are looking at kinematics, which is not having these explicitly, so it really doesn't matter. But as we already discussed in one of the earliest classes, the difference between the point and the particle is essentially in terms of its mass. Okay, but we'll keep it aside and just remember we are now only describing the motion. Okay, so we introduce a frame I, which is the observer's frame from which we are looking at it. No frame is inertial, but we assume this is inertial, and it's okay. And here we introduce, as we said, the first thing is the frame of reference. The second thing is the coordinate system. So you introduce your x, y, and z. So the first job is done, frame of reference. Second job is done, which is the coordinates, coordinate measure numbers. And then the third thing is the unit vectors. Unit vector is always tangential to the coordinates measure numbers, and in this case, because these are straight lines, it's quite trivial that parallel to the x-axis you have this I hat, we're calling it hat, right? Yeah. Okay, so I hat, similarly j hat, The hat essentially distinguishes unit vectors from regular vectors, which can have a magnitude different from unity. Okay, so that's all that the hat typically represents. I think it's a notation from your book as well. Okay, so the time derivative, as I said, it's kind of dicey, but with the way we have written, because we have not specified I. Strictly speaking, I should be putting a superscript I, pre-superscript rather, I over here, and I over here as well. Okay, both these first derivatives and the second derivative are taken when the observer is looking at it from the inertial frame of reference. Only then this particular thing is valid. Okay. Need more precision because derivative measures rate of change, and the rate of change depends on the frame of reference, which is what I'm saying here. Differentiation in which frame of reference, who is observing the change. In general, the differentiation in one frame of reference and another frame of reference chosen to represent the vector. So you see, for example, here we have chosen this frame I with the unit vectors I, j, k to represent one is in terms of the position, how to get to that particular particle through these coordinate measures, because that p can have the coordinates in general of x, y, z at a particular instant in time t, right? So we could, in general, when we are talking about derivatives, it need not be the same frame with respect to which we are taking the derivative. In this case, we are talking about, with respect to I, we are defining the position as well as the derivative of that position vector that we are going to have, which is the vector r. Now this vector r, its derivative, when we are talking about, let's say v, we are talking about the derivative of r with respect to t in this particular inertial frame of reference. It need not be. So you could use a different frame to specify your r, because remember that r is written in this case as x I hat plus y j hat plus z k hat, right? Now, because I'm using ijk and the measure numbers along ijk, therefore r is being expanded in that particular system. So for example, if I were to write r as a column matrix, I would just write it as x, y, and z, but then I have to specify that this is in the I frame of reference. Okay, it's because it's an I where I, j, k, and k are fixed. Therefore, I have to multiply the first row by I, second row by j, third row by k, and then add them up. Then I will get the actual vector. Okay, the same thing may not hold. And here, see that I'm not underlining it. So it's not a vector anymore. So it's not a vector anymore. So it's a column matrix, right? So this column matrix that you have over here is a particular representation of the same vector in a specific, when the frame of reference has been specifically chosen, the unit vectors have been specifically chosen tangential to the coordinate curves that have been introduced. So depending upon which coordinate system you have, which unit vectors you have, which frame of reference you have, this value can be different. Whereas the actual vector r will be the same irrespective of which expansion that you take in. So for example, I could have another x star I star plus y star j star plus z star k star, where the new set makes a certain angle with respect to this, maybe 1 or 2 or 3 angles of rotation about each one of these axes to get to the new frame of reference. And in fact, we'll be looking at some of those when we are looking at the aircraft rigid body dynamics. We'll be looking at the pitch, roll, yaw, how we can actually handle all of that, because remember that it's the same aircraft which is pitching, the same aircraft which is rolling and yawing to get to a new orientation, and that new orientation with respect to the original orientation, you have to get through what are known as one example is direction cosine matrices, etc., which will involve the cosines and sines of those angles through which it is rotating about each one of those axes in turns, and also the order in which it is rotating, about which axis first and then second and third. All of that will matter, which is why you might recollect I mentioned that rotation, especially finite rotation, is a vector which is one of the most complicated to deal with, but we will try to simplify and present it in the most easy to understand and learn way when we get there, right? Now, the only thing that I am repeating here once again, but because it's important, is that one, you have to have a particular set of unit vectors in which you are expanding R to get to something like this. The other is with respect to which frame you are taking this derivative, and in general these two can be different from each other. It's not necessary that both are the same, right? So yeah. So now, so that's what I was saying here, right? Yeah. Differentiation in which frame of reference, who observes the change in general, the differentiation in one frame of reference and another frame of reference which is chosen to represent the vector, which is what I mentioned over here. In this case, we are talking about the same frame over here. So with the corresponding coordinate system, if there were two, then you should have a separate coordinate system associated with that as well. Are there any questions so far? Okay. Next, we look at the inertial frame of reference Cartesian coordinates further. While differentiating with respect to the inertial frame of reference, again, you're differentiating with respect to time unless otherwise specified. The vectors that you have will be represented in Cartesian coordinates like what you have over here, and also in the inertial frame of reference. Then your I, j, k therefore are not changing because you're taking the derivative also with respect to the same frame of reference. The only things which are going to change are your measure numbers x, y, and z, I, j, and k being constants. Okay, when we do that, so it's very clear that three of the terms will drop off. Remember that in an earlier slide in the previous class, we had talked about this having not only x dot I, but also x times I dot. Okay, so that term I dot goes off. Similarly, j dot and k dot also vanish. So you just have only three terms in each, whether it's velocity or the acceleration. In one case, it's first derivatives with time, and the second case, it's the second derivative with respect to time. And both cases, you don't need to specify once again the frame of reference, because you have already taken that aspect into account by saying that it's the same inertial frame of reference that we are taking as the default, and therefore we are only interested in the scalar quantities being differentiated with respect to time, once for velocity and second time for the acceleration. Okay, now people tend to make it look kind of fairly complex, but it's actually a fairly easy generalization that you can go to from 1D to 3D. So because the way we have approached it with the same frame of reference for expressing the position vector as well as taking the differentiation, therefore the velocities and accelerations are defined with respect to the same observer who are observing the position. The same observer is observing the other two as well, velocity and acceleration. Now, assuming an inertial frame of reference and Cartesian coordinate system, which is just one level of complication from what we are already dealing with, rectilinear motion, therefore it is reasonably simple. So if you understood that, generalizing or extrapolating to this is not all that of a challenge. So if the acceleration, again, we are doing it in two steps. One case where acceleration is a function only of time, which is what we did, remember, in the rectilinear motion also, and we showed that it's the easy way to integrate, and within that also it looked at constant acceleration. But here we're looking at general function of time, but not of the position and the velocity. So when you do that, the 3D integration is equivalent to three rectilinear motions, because these are independent of each other. So I can treat it as three separate rectilinear motions, and then I can add them up. Because it's a linear problem, the principle of superposition is valid. I can deal with the x motions alone separately, the y motions alone separately, the z motions alone separately, and once I solve each one of them, I put them all together, which is one way of approaching this. But once you get to nonlinear problems, obviously you can't do this because the principle of superposition is no longer valid. You have to start from scratch with all these three motions being simultaneously present, and you have to solve for that. So if the acceleration is only a function of time, the 3D integration is equivalent to 3 rectilinear motion integration problems, as I just explained. Now, if the acceleration is also a function of not only time but also the position vector and or the velocity, just like the complication we introduced in rectilinear motion, then you will end up with 3 ordinary differential equations. Ordinary because still time is the only independent variable that you have, and whenever you have just a single independent variable, you don't have partial differential equations but ordinary differential equations. But nonetheless, because of the complication coming from PV, and there is a position vector r and the velocity v being affecting the acceleration, therefore now the ordinary differential equations are not separate or decoupled for x, y and z. You cannot solve each one of them separately and then stitch them together. Now you have to solve them simultaneously, which is what we call as the coupled system of ordinary differential equations that you have to deal with. And this is not again so very difficult, because remember, even in the rectilinear motion we were solving for, let's say, instead of going to r double dot, if we looked at just r dot and v dot as 2 separate variables of r and v, we were dealing with system of 2 first order differential equations which were coupled with each other. So it's not that big a deal, just that it's a second order system which is also coupled now. When you're dealing with everything in R, then also it is coupled. And so you have to solve these equations simultaneously, and it's not equivalent to solving 3 separate independent rectilinear problems and then putting them together. Okay, is this clear why this complication arises for 3D? Okay, now we'll take a step back now that we have understood the 3D motion of a particle. Before we venture into 3D motion of body, which will involve rotation, we will introduce the complication of not having a Cartesian coordinate system. So Cartesian coordinate system, what was the advantage that we got? Throughout, as you move along the x-axis or y-axis or z-axis, and therefore anywhere in space, your I, j, k were constants. So in other words, I can just move this origin to any other location without rotating this system. I can have an ijk there, and I will see that ijk at that point is the same as that at this particular point O. So everywhere it remains the same, ijk remains the same. Therefore, when we are taking the time derivative, we didn't need to bother about I dot, j dot and k dot. We only needed to bother about the measure numbers time derivative, that is x dot, y dot and z dot. Now that we might have problems in which the Cartesian coordinate system may not be a natural enough system, might only complicate problems in terms of the overall derivation, we have to introduce in 2D, for example, a polar coordinate system, which is r theta, and in a 3D case, just bring the same thing that we had in the Cartesian, which is z, and along with the polar, and therefore r theta z is the cylindrical coordinate system. Okay, so if we understand the simplest generalization from Cartesian to curvilinear, then other things are much easier to understand, because anyway you have looked at polar coordinate systems, the r theta kind of system quite frequently even in your schooling, and therefore it's not all that tough a thing to deal with, right? Now coming to the polar coordinates, it's very easy. You can see that you can do the transformations. So in the same thing, if you're looking at, for example, if I have both the Cartesian coordinate system and the polar coordinate system, you can easily transform from one to the other. Okay, so if you knew x, y and z, the I, j, k directions, the magnitude of the distance between essentially the displacement vector magnitude, which is the distance between those 2 points, namely the origin of the set of axes that you have introduced to the point that you're interested in, and that's essentially your square root of x squared plus y squared plus z squared, which is going to give you the magnitude of this r. And by dotting it with the I hat, j hat and k hat, the r vector, you can get the angles with respect to these, because remember that the dot product involves the cosine of the angle between the two vectors that are being dotted, which is the dot product in the dot product. So now that those angles are known, so you can essentially see that if it's a plane, this is a 3D problem in which will require a cylindrical coordinate at least. But to start with, we are looking at just a planar problem, in which case we don't have the z complication, we have only x and y. So when we are having something like that, so let me just erase to make it a two-dimensional problem, which is a planar problem in the plane of this whiteboard. All that I have to do is to get rid of this over here and this over here. So this is what we have. So it's a simple problem that we are starting, because we are trying to venture into something which is not Cartesian. Okay, the simplest case being the polar coordinate. And so the same point P can, instead of being expressed as in terms of the coordinates x, y, is now being expressed in terms of the again two coordinates but different. One is r, the other is theta. R is the distance that it is from the origin, and theta is the angle that connecting line or the position vector makes with the x-axis. Okay, so that is the theta that we are talking about, this particular angle, and then you have r theta over there, right? Now if you look at the position vector of the point in 2D space, it's represented by two coordinates, whether it is Cartesian or polar, because it's a two-dimensional motion that we are looking at, and therefore equivalently we can use either x comma y or r comma theta. Okay, so it's depending on the problem. One might turn out to be simpler to use for the entire derivation compared to the other. The major difference in the type of the system itself is because of here both were of the same dimension, which is the length dimension. So if you used SI units, for example, both x and y would be in meters. On the other hand, in the polar coordinate system, you have a distinction between the two measure numbers. One is in meters as before, just like x and y. R is also in meters. It's a length dimension. But the other one is non-dimensional, or if you're looking at in terms of SI, you typically express it in radians, right? So that is your theta. Of course, you can express it in degrees, you know the conversion between the two, pi radians being 180 degrees. Now, these coordinates, as you might very well recollect from your basic high school math, you can see that x and y can be obtained as r times cosine theta, r times sine theta, which is very easy to see from this triangle that you have, because this is the angle is theta. So the opposite side is y and the hypotenuse is r. So y divided by r is going to be sine theta. Similarly, x, which is the adjacent side, divided by the hypotenuse, is going to be the cosine, which is what you see here. And then you see, instead of x by r, you are bringing the r to the right hand side, and therefore you are having x as r cos theta, y as r sine theta. Very easy to see. As we already mentioned over here, the magnitude of this is, because it's a Cartesian coordinate system, very simple. So sum of the square root of the sum of the squares. In this case, there are only two quantities, which is x and y. So square root of x squared plus y squared is what you have as r. And this is always positive because it's a distance from the origin, irrespective of which direction it might be in. Here we have shown it something in the first quadrant. Even if it's the second, third or fourth quadrant, your r always remains positive. It's only the theta which changes depending upon that. So you can very easily see from 0 to 90 is your first quadrant, 90 degrees to 180 degrees, or rather pi by 2 to pi radians is your second quadrant, and so on and so forth. Right? Now, how to get that theta? For that, very simple. Once again, just like we looked at sine theta and cos theta, we look at tan theta, which is opposite side divided by adjacent side. The opposite side happens to be y, the adjacent side happens to be x, and therefore y divided by x is tan theta. We take the inverse of that, and therefore theta becomes tan inverse of y by x. So here, this set of equations in the, that we have here, this one and this one, given our theta system, you can convert it to xy. This is the other way around. Given your x and y, you can convert it to r theta. So they are easily interchangeable from one to the other. But now a problem comes in this particular quantity because it's arctan or tan inverse, and that should take into account the correct quadrant, because otherwise especially when you're implementing it in a computational thing, the computer can get confused and you can have multiple solutions. So only one of them is realistic from a physical perspective, and therefore you have to bring that into account. So languages like computer languages like Fortran, for example, introduce, instead of a tan alone, there's a concept called a tan 2. It's a function introduced as long back as 1961. So this is something that is quite routinely handled by most computational systems. Not to worry, but if you're writing your own code, you have to keep this in mind. Okay. Are there any questions so far? Okay, this is just a review of what you already know. So why that is a problem? Of course, it's quite clear that what happens if you plot this particular function, you could have multiple values. For the same value of y by x, you could have either this value or this value, right? So if you take the same value y by x equal to -3, for example, you could have either close to minus half pi, or you could have close to plus half pi, a little more than that and a little less than that in this case. And therefore there is a you don't know which particular quadrant you're in, but the physicality of the problem is something that you can reason out and say one is the appropriate one, the other is superfluous. It's not of significance for the physics of the problem, purely a mathematical result. Okay, so which is what is taken into account by some of these functions to take the physics into the picture. Okay, now that we have understood in 2 dimensions, that's just x and y, we reintroduce the third dimension z, which is along k, and therefore, and that is the same irrespective of whether you're talking about the polar coordinate system or the Cartesian coordinate system. In the Cartesian coordinate system, we had x, y, and for the 2D, and r theta for the polar, which were both different. Now when you're introducing the 3D, the third dimension is the same for both, which is z times k hat. Okay, so it's not going to be overly complicated, and this is again something that you should be familiar with from high school. So the position vector of a point in 3D space is represented equivalently by alternate coordinate systems. In this case, we are also talking about the spherical. Let's leave that out for now. We are essentially talking about the first two, which is the Cartesian, where we are looking at x and y, instead of which we had r theta. Now we are adding z to both of them, which is the same z, and therefore in terms of the transformations, it's exactly the same transformation we had between polar and Cartesian in 2D, just that because the third transformation that we have is just trivial, that you are replacing z with z, it's the same quantity. Okay, so now of course there's also spherical coordinate, sometimes might be useful, in which case like what Lalita brought about in the morning, talking about latitude, longitude, etc. Then you have this with the r. So then the third coordinate is also going to be different, and 2 of them are angular in radians or non-dimensional. One of them is having the dimension of length, which is r. So right now we will not go into the equations of that. Okay, or maybe we do, I don't know. Okay, so math, again, in terms of the spherical coordinates, there's this distinction that you should remember. Mathematicians use a particular way of representing it, and the physicians or physicists use it in a different way, which is brought about in this particular distinction that you see over here. So there's an interchange of this theta and phi that you see in these two. So this is phi over there and theta over here. This is for how the mathematicians do it. This is how the physicists do it. There's nothing right or wrong about either one of them. It's just that you have to be consistent. If you follow one particular system, just follow that. There's nothing wrong in either one of these systems. Just be aware of that. Because when they write it, they will write it in the same order, r theta phi. Here also it will be written r theta phi, just that the values will be interchanged because the angles that they are considering are quite different. R, of course, is the same in both. Okay, now we're looking at the polar coordinates, a vector transformation for them. Okay, so now that we had the unit vectors in the Cartesian coordinate system, ij. Similarly, we introduce unit vectors for the polar coordinate system as well. This is along the r and the theta. So r, remember, is the radial distance. So along that particular direction, we introduce a unit vector. This r, as you see, is having a magnitude which is not necessarily 1, but parallel to that, if I introduce a vector over here, I will be calling that as E r hat. And like before, hatted quantities all have a magnitude 1. It's only the direction which is different, and the direction is always going to be from the origin, which is O in this case, and going outwards. Okay, so that's the direction. So inwards would be minus or negative er hat. The outward will be er hat positive. Okay, now the e theta will be in the direction in which this theta, remember, is positive, taken from the x-axis. That's how it's measured. So as the theta increases, that particular direction is what we call as e theta hat, and so therefore you will have a unit vector along this, which we'll call as e theta hat. Okay, so that's what we have over there. And once again, just like we had, remember, the transformation from xy system to the r theta system, that is, we were transforming the coordinate measure numbers. Given x and y, I could determine r and theta. Given r and theta, I could determine x and y. So vice versa was also possible, right? Now here, given I and j, can I determine er and e theta? Or given er and e theta, can I determine I and j, all hatted quantities, is what we are trying to look at over here. So the transformation is very, very similar. Again, this is something that you would know, so I'm just revising that. So for example, if you know I and j, then you can get er hat as cosine theta times I hat plus sine theta times j hat. You can look at it from special cases where theta equal to 0, then you know that if theta equal to 0, the position vector will be along the x-axis, and therefore it should have only a I. Then you can see that the sine theta would go to 0. It's only cos theta which will be 1. Cos 0 is 1, and therefore you'll see er hat is equal to I hat when theta equal to 0. The other extreme, you look at theta equal to 90 degrees, then you have cosine of 90 degrees or pi by 2 radians is 0. So this second term vanishes and the first term alone remains, and then you would see that e theta is going to be minus I hat. You can see why it is minus I hat, because it's this way, remember, in the increasing theta direction. So once this vector rotates and comes to the vertical direction, you can see that this e theta continues to go in the same way, and it will end up as a negative j hat, which is the negative I hat, which is along the negative x-axis. Okay, so and of course this is valid for any theta in between or beyond that as well, all the way from 0 to 2 pi radians. Now, next thing that we would like to know here is that these unit vectors that are there in the polar coordinate system are not the same at all the points in the frame of reference. Very easy to see. Already we saw here it is having a particular angle here. Already we saw if it was this particle was on the x-axis, it will just be I hat. That is what er hat will be, and so er hat will become j hat when the particle is on the y-axis. So depending upon where the particle is, you will have the directions of er and e theta changing. Of course, they are unit vectors, so their magnitude doesn't change. It's only their direction which changes, but that's enough for a vector to change. Either the magnitude or the direction or both should change, and since the directions changes, er hat and e theta hat in general, you have to express as a function of theta in this case. It doesn't depend on r, because if you have different magnitudes of r, you will see that the direction of er hat remains the same. Similarly, with your e theta hat also, it's a function only of theta, not of r, right? So unit vectors in the polar coordinate system are not the same at all points in the frame of reference, because they depend on the actual angle theta that position vector makes with the x-axis, which is what we defined as theta. Unit vectors depend on space, though not on time. So why do they depend on space but not on time? Because the dependence on time is through the space, not explicitly on the time alone. Okay, it doesn't matter if you're going from one time instant to another time instant, as long as you're at the same location, you have the same ER hat and E theta hat. Okay, it's only the location which determines these two, and amongst the location also R doesn't determine it, it's only theta which determines it. That's all that we need to remember. So unit vectors depend, of course their magnitudes are always one, but talking about the direction, even the direction depends only on space and not on time explicitly. Okay, through space it can depend on time, because the same particle at some other time might be over here, and then you might say that see ER and E theta changed with time. No, it didn't change with time, it changed because of the position, which in turn changed with time. Okay, so that is important to remember the cause in an appropriate logical fashion. Okay, so the particle moves in space, therefore the unit vectors change, and which means that the vectors corresponding to the moving particle, say the position vector or the velocity or the acceleration, things that we are interested in from a dynamics perspective, these particle represented by unit vectors will also change with respect to time. Because the unit vectors are changing, they will also change with the time as well. Okay, so that's important to remember. Whereas the unit vectors depend only on space, all of these, the position vector, the velocity and the acceleration, these will, because the unit vector has changed, they will change with respect to time. Are there any questions? Yes, Grace.
The slide beforehand, I missed what SPH stood for. Sphere.
Yeah. Okay. Anything else? Anybody? Okay. Okay. Now let's consider the motion in 3D space. Now we have this vector, let's say P of t, which represents the position vector, once again in the non-existent inertial frame of reference, for which we have reasonably good engineering approximations. And then now, because we're using polar coordinates, it's no longer x times I hat plus y times j hat, but still it's on the plane. It's a planar motion that we're looking at to start with. Then you're having only this R of t ER hat. But once you bring in 3D motion, you have into the plane of the screen or out of the plane of the screen. That's what is represented by the second term over here. Now we have a way of handling general 3D motions using this new coordinate system, that is the r theta z coordinate system that we have, which is just extrapolation or generalization of the polar coordinate system that we already looked at in the previous slides, where we had only r and theta. Now we have z as well. So once again, you're seeing that your k hat is not explicitly depending on time, but your z, the position vectors measure numbers, be it r of t or z of t, are depending on it. Very intriguing thing going from Cartesian to this is that in Cartesian we needed 3 terms to represent 3D motion, xi plus yj plus zk. But here we need only 2, because the first one takes care of both. This entire thing xi hat plus yj hat is together your r, the vector r, okay, which is along er hat. So there's nothing along e theta hat, but you will get e theta hat components for the, let's say, the velocity and or acceleration when you take the derivatives, because remember that er and e theta will change with respect to theta, and so derivatives will also, theta in turn is a function of time in general, and therefore you can end up with that kind of a complication. But the position vector looks very, very simple. And in fact, when you go to spherical coordinate system, it's even more simple, because even this term drops off. You'll only have r of t er hat, which can identify any point anywhere in space, because er hat has that angular information. Remember that just like here, er hat is a function only of theta, there in a spherical coordinate system, it's a function of both theta and phi, the latitude and the longitude. So then you would have theta and phi essentially contained inherently, implicitly in your er hat. So it's not that p of t is not a function of theta in this case, or theta and phi in the case of the spherical coordinate system, just that it's all contained within your er hat, and therefore you don't see it explicitly in the expression. So therefore you will have only 2 terms. One is to identify at z equal to 0 the projection of that point onto the z equal to 0 plane which is what is this term, which is a polar coordinate system and which is good enough for a 2D motion. Now for 3D motion, you're going away or into the plane, and therefore you have positive or negative z of t times k hat respectively. So now that we have that, we will see that, yeah, this is what I was trying to explain, that theta is implicitly contained in your ER hat, has just we pointed out here that ER hat is different. Depending, it's aligned with I hat if it's on the x-axis, aligned with j hat if it's on the y-axis, and anywhere in between if includes both components if you're anywhere in between, right? So that theta of t is coming in implicitly over there. Now coming to the velocity and the acceleration, starting with velocity, as always, it's the time derivative of the position vector, but with respect to which frame, again that's important. So once again, it's that same inertial frame of reference as the default that we are using to describe both the position as well as the derivatives, and therefore we are not explicitly stating, but strictly speaking, I should be putting an I over here as a pre-superscript. Same over here also, I should be putting I as a pre-superscript. So you can again see that V dot, you can replace V as P dot, and therefore it becomes P double dot of T. We're just using P instead of R, it's the same thing, okay? It's a position vector. Now, because of the fact that these two unit vectors, ER hat and E theta hat, are going to change depending upon theta, it's going to change. So it started off over here, it went on like this, and when it comes, the particle comes towards the y-axis, it becomes like that. One is negative I hat, the other is positive j hat. So because of that dependency on theta, we'll have a few complications coming in. Here it looked very simple that instead of 3 terms, you have just 2 terms. But here when you're taking the derivatives, because ER is a function of theta, you're going to have the complications setting in. Okay. The velocity, for example, is the first time derivative of the position vector with respect to the inertial frame of reference. And when you do that, you have to take the time derivative for all the quantities which change with time. And if you look at this particular equation, the position vector, it depends on R, it depends on ER hat, depends on Z, it depends on K hat. K hat doesn't depend on time, but ER hat doesn't seem to depend on time, but because it depends on theta and theta depends on time, therefore ER hat also depends on time, okay? So one of the unit vectors doesn't depend on time. The other 2 unit vectors, of which only one is appearing in this equation, namely ER hat, E theta hat is not appearing in the position vector. So that is going to be a function of time, and we have, when we take a time derivative, we have to treat this as a product of 2 functions of time. We take one at a time, we take the derivative, keep the other the same, okay, which is what we do here. As you see, first we take the time derivative of R, that is over here. Here it's a scalar measure number, doesn't matter, so we don't need to specify the frame of reference, and keep ER hat as it is. Now we have to do it the other way around, keep R as it is and take the time derivative of theta, ER hat. So we keep R of t as it is, and then we take the time derivative of ER hat. Now this in turn can be done in 2 steps, because ER hat is a function of theta and theta is a function of time. So we can take the derivative of ER with respect to theta and then theta with respect to time. We'll come to that. As far as the second term is concerned, it's very, very simple, because K hat is not a function of time. So the only function of time is Z of t. So I have to take the dot of that, which is Z dot of t multiplied by K hat as it is. Coming to the acceleration, we have to take one more time derivative, this time of the velocity vector. And when we already have an expression for the velocity vector. So when we do that, we get, once again, whenever there's a product, we have to take one at a time. So first R dot becomes R double dot, ER hat remains as it is. The second term, R dot will remain as it is, and then ER hat will have a dot. We will see that one more term, similar term, is coming from this. When we take the derivative of this, once again, both are depending on the time. So when I take the derivative of this with respect to time and keep this as it is, it's the same term which we got over here, and therefore you're putting a 2 over here, a prefix 2, multiplying that, so we get that quantity twice. There's one more thing that we have to do here, that keep this the same and get double dot of this, which is what you see over here. R is as it is, and ER hat dot has become double dot because you're going from velocity to acceleration, you're taking a time derivative. Finally, the last term, as simple as before, k hat remains as it is. It's only z, which is a function of time, and therefore z dot is also a function of time in general, and therefore you have a z double dot, which is a function of time times k. Okay, we will look at some of the meanings of these new terms that we have got. They have certain relevance and some things that you might also be familiar with from different concepts before, but we are expressing all of this in vector form, so some of these things might seem new to you, but actually many of these things are something that you are already aware of and will become clearer as we go forward. Any questions on this slide? Fine, let's go. So differentiation of unit vectors, because we need, remember in the slide, we have not yet completed this expressions for v of t and a of t, because they are still in terms of the dots of these unit vectors. Er hat dot here, and er hat double dot over here. But remember, if you go to the slide even before this, we have already got expressions for er hat and e theta hat in terms of I and j, and we know I and j don't change with time. It's only theta which changes with time, and we know that this can be easily handled. For example, I can put this cos theta derivative as minus sine theta times theta dot if I want to take the time derivative. Similarly, the other terms, so which is what we will invoke now. We will use that expression along with these expressions in order to write this out purely in terms of er hat, e theta hat, and k hat. We don't want the dots on the unit vectors to remain. Okay, so we want to get rid of the single dots and the double dots on the unit vector. In this case, only er hat is there, no e theta hat. So we need to differentiate that expression that we had for er hat. So rewriting that, so you have this differentiation of unit vectors. So you have er hat and e theta hat. Even though we don't need e theta hat dot right now, it might be useful to do that as well and keep it handy when we need it. Okay, so differentiating with respect to time and knowing that your Cartesian coordinate unit vectors I and j are not dependent on time, it becomes quite straightforward, because you have to once again employ those chain rules and also product rules, and wherever they are necessary. And when we do that, you see, for example, your er hat dot is going to be just a theta dot times e theta. In fact, you will see that you will get from this term a minus sine theta times theta dot, and you will, from this term, you will get a cos theta times theta dot. And then if you remove the theta dot out, then you will see that what is left is your e theta hat, and which is what you're going to substitute there, which is why it looks innocuously simple here, that it's just theta dot times e theta hat. Okay, so you started off with theta dot times two terms, okay, within brackets, but those two terms add up to give your e theta hat, and therefore you just resubstitute that, and it's very easy to intuitively see what is happening here as well. It's essentially you're looking at how this unit vector er hat is changing with respect to time, okay, because dots are always with respect to time. So you know that unit vectors magnitude will not change, because they are by definition unit vectors magnitude of 1. The only way they can change is through time, through the direction, and in this case er hat, if I move this slightly by a small angle d theta, then you see that it's going to be like this, and you see that this is your new ER, which is essentially just rotating about that angle, which is what you're seeing, that the direction in which it is happening, that change, is actually your E theta. Okay, so that's what you have as ER dot. ER double dot is a little more complicated, so because now you have to take once again the dot of this, and then the keep this as it is, then you keep this as it is and take the dot of E theta. When you do that, you get this particular expression as I just mentioned, and then you have to substitute for E theta hat dot, which can be expressed in terms of ER now. And once we do that, we have two terms, one which is the coefficient of E theta hat alone, the other which is a coefficient of ER hat alone. Okay, I would encourage you to do the one or two small missing steps in between, and you will see that these are all fairly straightforward differentiation of two quantities which are multiplying each other. So you have to take it in that particular order, those rules that you employ, then you will see that this is what you end up with. Okay, so we now have the first derivatives of with respect to time of both ER hat and ER hat double dot, which is the second derivative, that is, and both of these are taken in the same inertial frame of reference in which your ij are fixed. Okay, and with respect to which, of course, your r theta system is also defined using the x and y. Now the final expressions, once we substitute for these into the what we had in the previous slide, or what we have rewritten over here on the top, so we have to just substitute because the only things we wanted to get rid of were the dots on top of the unit vectors, namely ER and whether it's a single dot or a double dot. And now we have expressions for both of these from simple math, taking derivatives of products. And once we have substitute that there, this is the expression that you have for the velocity and the acceleration. So the velocity is having terms, some of which might seem intuitive to you, some of which might not, but we will get to that. We'll look at the practical aspects of that. We'll look at the meanings of each one of these terms in the next class. But right now, it suffices to say you're looking at various phenomena which is of great significance in engineering in general and aerospace engineering in particular, and some of which are coming to prominence over here in terms of the mathematical beauty of those particular physical phenomena. So first thing what it is saying is that if you're looking at the velocity of a particular particle in the cylindrical coordinate system, so it's 3D motion that we are dealing with, one thing that is obvious is z dot times k hat. Okay, so that's quite straightforward. The remaining is coming purely from your polar coordinate system. One is because your radial distance is increasing. So this particle, for example, could be just moving on that curve, and so just on that wherever it is currently, just increasing its distance from the origin, maintaining the same angle with respect to the x-axis. That's essentially what you have here as an r dot times er hat, because the direction in which it is er hat. That's how we have defined er hat, the radial direction, the unit vector. So it's just increasing or decreasing your distance from that. That's what you're seeing over there. Now the second term, slightly less intuitive, but something that you can actually perceive over here also. You're looking at what is happening when theta changes, because that's what is theta dot. Okay, so when theta changes with respect to time other than r, so you are going to have this particular position vector is going to rotate, just like we drew the dotted or dashed line over here. So that's what has happened. And so when it is happening, you can see there is a change that is happening over here, which is in the direction of E theta, which is what you see over here. It's moving in the direction of theta. That's what you see over here, right? And how much is it moving by? It's essentially the distance, which is essentially for a small angle, you can think of it as the distance times the angle change that is happening. That change is your d theta, right? And it is happening over a time dt. Okay, so that's your r d theta that is happening. So if you look at this small distance that it has moved, it is parallel to your E theta hat direction, and it's given by the distance from the origin times the angle change, which is a small angle, which is your d theta that has happened. So it's r d theta, and is happening over a time t, and which is what we want, because it's per unit time we want to determine. That's your velocity, how it's defined with respect to the displacement. So displacement per unit time. So r d theta divided by dt, and d theta by dt is nothing but your theta dot. So even though this is a purely mathematical derivation, you can look at it from the physical perspective also in order to understand that. While the velocity is quite straightforward to see it from that perspective, the acceleration is not, and we will revisit this and give specific names to each one of these terms in the future classes. But right now, it suffices to say that just like the velocity, this also has three components. The third component is the simplest as before, which is just the double dot of z times k hat. It's the other term which is slightly looking kind of difficult or weird because some things are quite clear. For example, if you're looking at the radial direction, it's r double dot should be there. Okay, so r double dot is how you're accelerating on just on that particular line joining the origin to the particle. So r double dot is very clear. So here this may not be very clear to you. Now coming, but once I say what theta dot is, it becomes clear, because theta is the angle, theta dot is the angular velocity. So in looking at angular velocity squared times r, omega squared r. So that's something that you're very familiar with what it actually is. Okay, we will name them depending on the sign a little later. Okay, but that is contributing towards your ER hat as well. Okay, this is because you are having two different kinds of dimensions. One is a length dimension, the other is a angular dimension in your coordinates r theta. Okay, z of course is again length, which is the simplest to have. Now coming to the acceleration that you have in the angular direction, e theta hat direction. What is the acceleration parallel to e theta hat? Again, you have two terms. Just like you have two terms along the radial direction, you have two terms along the angular direction as well. Again, just like the first term was quite intuitive, because along ER hat you should have an r double dot. Here also a theta double dot along e theta is quite intuitive. What is the angular acceleration? So you have a theta dot which is omega, then you have a theta double dot which is our angular acceleration alpha. So you see that alpha times r should give you that particular acceleration. What is not so very clear is this. Mathematically it's clear because this derivation we have walked through, but from a physical perspective what it is, we will come to that. So it is 2r dot times theta dot over here. So what these two specific terms mean and some examples related to that we will take up in the next class. So with this I'll finish today's class. If you have any questions, I'll be happy to answer. Okay, thank you then. See you online on Wednesday.
Wednesday we have
On Wednesday.